He has like a physical.
I'm still working with this. He's still working with
Alright, everyone, we're gonna get started now. Yeah, okay. So that's coming in. There's water. Did Dimitri scare you that much?
He just like appeared.
He just appeared?
Running. He can be scared.
He can be scared. He is Russian. He's rushing out the door. Alright, so this is Austin Deep Learning. Just quick show of hands whose first time is here. Okay, we're getting more and more regulars, so that's good.
It's not warmer in this room.
What?
It's not warmer in this room.
What does that mean?
I'm sorry, I thought you said warmer regulars, but you said more and more regulars.
More and more regulars. Warmer regulars.
Yeah.
That's an interesting take. I wonder if Whisper would have caught that one. Okay, so this is it's Austin Deep Learning. We're sponsored by Cal Factory and Antler. Cal Factory is a space, and then Antler is a they don't call it an accelerator, but we'll use that word right now. So if you parked in the garage, just raise your hand if you parked in the garage. I'm going to give you one of these passes. So you pay $8 and not 50 something. It used to be 48, but inflation. So there you go. There you go. If you don't mind passing that down. And what did you? Anyone else?
Monday and Tuesday, you can park on the street.
Yes, you can park on the street.
Street parking is free.
After 6.
Monday and Tuesday.
Yeah.
There's plenty of people out there watching our cars. Dimitri, did you park in the garage?
No, not today.
Not today. Okay. All right. And again, every time I ask this 100 times, someone will come up to me at the end, chase me down, and be like, "Dude, can you park in the pass? I don't have it anymore." I don't actually print these out in my mouth, so make sure you get it before you leave this room. So we usually meet on the first Tuesdays. We're more focused on research, not talking in the background, and we do open discussion. So please, you can interrupt or just raise your hand and say, "Hey, I have some insight on that," or "Hey, I don't know what you're talking about." It's very back and forth. It's very multi to multi. This is not a lecture. Okay, so. There's parts of the paper, parts of the paper that Alex and I are both presenting today. There's parts of the papers that we probably don't fully grasp. And so, if you think you know something, just raise your hand. I'll give you 2 of these. Okay. So for next time. So Eric, do you want anything? No. Okay. So we're going to do 2 papers. So if you don't mind, you can Google that, learning to learn at test time, or you can just scan the QR code. If you're in the back and you can't scan it, you can walk up. There's no toll. Just scan that. I'll give you a second to pull up the paper. It's good to have as a reference. I'm gonna cite a lot of figures. So there's a lot of papers called TPT or learning to learn. It's a concept that's been around for a few years at least. This is the one 2407.04620. So first author is Goose. It's from this year, but this topic is actually much older. Yes.
Should do something before you start.
Right, go ahead.
So a lot of conferences have their deadlines coming up next week. So if anyone of you is a researcher, do take a look at like Colling has its deadline.
How do you spell that?
C-O-L-I.
C-O-L-I.
Yeah, Colling, right? It's like an NLP conference, and then Europe has a few workshop paper conferences this week. ICML has some conferences coming up. Has some deadlines coming up this week. So yeah, one of the conferences and deadlines coming up this week or next week. So
Okay.
yeah.
Okay, thanks for making it feel like we have a good deadline. I'm just kidding. No. If you guys have a paper that you wrote, you know, definitely do a submission to Dimitri. Set up and actually put it. The deadline's today. Okay. I see. Okay.
We got 5 hours.
You got 5 hours, so
Jump on it.
yeah. Don't pull. What's that guy's name again? Who like plagiarized paper? The big ML guy.
Yeah.
The guy who made the YouTube videos.
Wait, Siraj?
Siraj, yeah, don't do a Siraj and like screenshot this stuff and publish that. That's not cool. But no, I actually saw him in SF a year ago and I wanted to scream. So I'm gonna go to the first presentation. This is gonna be 30 minutes. So we're gonna stop around at 7:45. If I start running over that, you can yell at me. I won't get mad. Alright, so this one's called Learning to Learn at Test Time. Those of you who have the paper up can get the figures, otherwise, go figure. So we're gonna do a quick comparison with RNNs versus transformer attention blocks, right? So learning to learn at test time is a general concept that could be applied, I think, to any class of neural networks. They focus on RNNs in this paper, so just kind of quickly get everyone on board. The thing on the left here is for RNN. So the idea, so this is the output, this is the input, and then H is this hidden state, right? X and Y would be tokens in this language. The hidden state is something that you can't directly semantically understand. And the important point is this arrow. This is unrolled over time. So this is at point t. This is at t minus 1. This is a future t plus 1. So if you think the future prediction is dependent on the input and the past based on the propagation of the activations from the hidden state, right, and the previous inputs. So that's an RNN. You have to train it like a vanilla regular RNN. You have to train and inference it more or less autoregressively, sequentially. That's why transformers kind of took off. Just the thing on the right, because you can train them in parallel. And the way it works is it looks at all the data at once as making a prediction. Where here, after many of these sequences, it becomes goldfish memory and it forgets old stuff, right? Where here, you just have everything at once. So you just have a guy taking a test with a giant cheat sheet, right? That's what a transformer does with attention. An RNN is like someone who's actually studying, but they forget a lot of what they learned, right?
Can I
Yes.
say my understanding about the big difference
Yes.
between RNN and CNN is that RNN has to decide what they keep and what they forget
Yes.
at the beginning, but transformers can decide at the end what is important and what is not in
Correct.
all the past.
Correct.
So if in your transformer there is like the whole Harry Potter book, and at the end the question is, what was Harry doing on page 7? The transformer will be able to find this information, but the RNN doesn't know which information will be important according to the question at the end, so it doesn't know what to keep and what to forget.
Right. So until you're tested on something, you may not know what's important. And like you said, the transformer uses attention blocks, which attend to what is considered important at the point of testing. Where in an RNN, it just happened to have kept that state. If it didn't keep that state, well, it's gone. Now the benefit of an RNN though is that state, the hidden state, is fixed in size, so it doesn't grow. So if you want to have a really big input sequence for a transformer, you have to have quadratically more complex memory. Or with an RNN, you don't, right? So that's why in this paper, I think they wanted to really focus on RNNs because they wanted to have that advantage of having a fixed hidden state size. Which brings me to parametric versus non-parametric learning. So the first, ML algorithm that I played with a long time ago was k-nearest neighbors. Is anyone here familiar with that? Okay. So k-nearest neighbors, I like to talk about it because it's really simple. There's a bunch of data points, and I'm gonna use colors to represent classes. You just have a bunch of data points, and this is in a hyperspace. And then we get this new data point. These are all the training data points. And then you get a new data point, and maybe it's right there. And you say, okay, well, which classes does it belong to? Black, blue, or red? And you say, oh, well, it's probably black because it's the closest, right? You're not really learning weights. This is a non-parametric model. So you're not learning any model parameters. You're just comparing an instance to other instances, right? And so they make a comparison to that here, to KNN in this paper, and that the attention mechanism in a transformer is attending to basically these instances. And that cache, or that state is represented as a KV cache in a transformer. And so as you grow the input size, or the token index, you increase that KV cache. When you increase the input sequence size in these parametric RNNs, you don't do that, right? So an RNN, a Mamba is based off of RNNs. RWKV is RNN with key value cache. And then LSTM is a more explicit version of what Olivier was saying, where it has to know what to keep and forget. And then for non-parametric, we have these self-attention based transformers. So they make that contrast here. So in a forward pass of an RNN, this is not during training. This is during, I'm talking about only when you're doing testing or inference. You're not doing weight updates. So basically you train this model, and this is true for, even, Llama, whatever, or Mistral, whatever, or any, ResNet-based CNN, whatever. They just train a model during training time, and that's, training means you're updating parameters, right? And so you're calculating some gradient, and you're updating the parameters so it gets more accurate over time. And then once it's done, it's just frozen, and then you go ship it off into inference, into production. And that's what's happening here. So A, H, O, and Y are the activation, hidden state, output, respectively. At no point are you updating the weights. The weights is W. You're not updating it, you're just using it. And you use it after it's been trained, right? So that's just a forward pass of an RNN. You do this over and over and over again, regressively, and you can produce a sequence from an input sequence. Now, what this paper talks about is TTT, test time training, which sounds like cheating, but it's not cheating because they use fancy math, right? So, so what test time training is, unlike here where W doesn't change, here W does change, right? So W at T is based on the old value W, and this is just like a gradient descent update, right? And so you're updating the weights based on previous values of the weights, inputs, and outputs. So that's fundamentally what test time training is. So what it is online learning. It's like offline learning. Again, this general concept, I don't want you to get hung up on RNNs with. I think you could do this for any other class of models. So let's look at the results really quick, because that's like the money shot, and then we can talk about how it works. So what we see on the right here is with a longer context size, right? So this is, I think this is 32K, yeah, 32K on the bottom right, you can see. It goes up to 32K. So TTT is the blue one, and then on the y-axis we have perplexity, which is basically a negative thing, so you want to minimize it. So lower is better, lower is better. And if you notice, it kind of saturates for Mamba and transformers, the green and red. After some point around here, starts to flatten out. But it keeps going down for the test time training system, right? And again, on the left, we have, this is just compute power, this isn't flops. So these are all faring well in terms of compute power. We can keep scaling compute. This is when people say, oh, well, transformers are amazing, because you can just keep throwing more compute at it, keep throwing more compute at it, 100,000 H100s, 1 million H100s. We won't break Taiwan, I promise. Just keep doing it, and we'll keep getting better. We'll keep getting better performance. So you can still get better performance with TTT. It doesn't take away that advantage. But the benefit is you're actually minimizing perplexity or loss in a sense as you increase the context width, right? That's a problem with RNNs. You keep increasing context width, you start getting worse performance. So this is like a big important part here, and we're trying not to. We don't want to lose that benefit. And then here we have latency. So this is seconds per token, not tokens per second. So this is the inverse. So here, again, lower is better. As you increase context length, that KV cache grows in a transformer, and also the capacity of the transformer inherently has to be greater. And so that means it's slower, right? That's why the little 3V model is gonna be faster than an 8V model. So, what's cool with these, yes?
Does that speed implication have anything to do with what the retrieval time from the cache is, and is that size-based?
Well, so the idea is that if you notice the bottom axis is context length, so as you increase context length, you need an ever more powerful transformer model that can store quadratically more memory. Where with a TTT model or a Mamba model, the cache, like you're saying, is consistent in size. So you're not actually increasing the requirements on RAM to process this larger sequence.
You know, that maybe the question is ill-formed, but if the cache grows quadratically, is the time to access it going to grow quadratically, or does it grow at a different speed?
I believe so, not 100% sure.
Yeah, I mean, that's what's causing it, is the growth in the cache size and the search time process.
So it's linear in cache size?
Yeah.
Okay, thanks.
Alright, so, next one, this is pretty cool.
Actually, could you go back?
Yep.
For a second? Okay, yeah, the scale on the bottom is linear. Okay. So
Are you saying the KQE computation, the linear layer computation?
He's asking if cache access is linear as context length increases.
So if you've got quadratic.
Because this
quadratic
figure shows that,
growth,
right?
it's
So-
space, but you have, linear cache.
Yeah.
Is that necessarily the case if the cache is designed differently?
You could learn from the cache and have a TTT system.
You can work on the cache how to, I think that's what we do. Not sure. But I mean, this figure is linear on both axes.
No, that does make sense, what you said, that it's, the memory space grows quadratically, but cache time grows linearly.
Linearly in cache size, which means quadratically in context length.
Yeah.
Quadratically in memory consumption, but not in retrieval time, right? Retrieval time is linear. So like if you increase the context length linearly, retrieval time is linear. But if you increase context length linearly, memory requirements are quadratic. Right. Cool. So left versus right. Left is 2K token with context, and the right is 32K. So in 2K, there's not a big difference between TTT versus transformers. Transformers is the purple one. That. And the TTT are all the other ones except for the red one. The red one's not one. So they're pretty similar-ish, but when we start looking at these really long context widths, and by the way, the models are using our 1.3 billion parameter models for all of these. So for the right part of the figure, the scaling trends seem to produce a much more pronounced effect when you're looking at TTT and Mamba versus transformers. Right? So transformers is the purple one. So we're looking at about 3.5 times fewer compute measured in flops to get the same level of complexity. Right? So at this level. So that's great. That's a good result. And then they have these two different types of layers and the TTT approach. They have linear, which is just a forward projection, and they have MLP, which is the nonlinear projection. And the nonlinear MLP one runs a little worse until it starts to get around like 4K, 8K context one, and then after that, this it starts to outperform all of the other types, right? So they call this token index because they're measuring the perplexity of the next token as you keep increasing this order aggressively. So it's not just merely size; it's as you scale out that, as you fill that context out. This is a general way to depict sequence modeling, and then they show in figure 4 the 3 different ways to implement the update rule, output rule, and the initial state. So this is really similar to that figure I showed you earlier, right? This one, right, for RNNs. But they just generalize it for RNNs, which is the top row here, self-attention, which is what transformers use, and then native TTT, test on training. Again, difference between these two is that you're updating the weights. But everything else is about the same. But what's cool is again you get this cost, which is O of 1 in complexity.
What is the logic behind the weighted base at this time?
The logic is that you want to do weight, so it's test time, right? So the idea is that you're updating the weights of the model as you're inferencing it.
But at this time you don't have the label.
So the idea is that RNNs have that context that they manage for the hidden state. But one of the ways they want to circumvent the issues with it forgetting information is they actually want to update the weights of the system. So you can learn new activations for the same inputs.
With my understanding is that you need the ground truth to the
Yeah, they still have that. You'll see that in a future slide. They're still in ground truth because you're doing in self-supervised learning. You're doing X token prediction, but they're doing a reconstruction loss against the current token. So they do have a ground truth. And they actually separate this as a meta learning concept, as I'll show you later, where they have an outer and an inner loop for training. So they do self-supervised for outer loop, and then reconstruction for inner loop. So there is still a label. Yeah.
What does the update rule mean in terms of self-detection? Like, what are you updating and testing?
So S is a sequence, so you're saying the sequence S of T is the old plus the predicted new token.
Can you outline the KV cache? The KV cache?
Yeah.
Like, well, what is it updating?
The KV cache.
The KV cache. That's basically the state internally, right? So you're saying like the new state ST or current state is the old state plus the KV cache prediction of the current. That's it.
Got it.
Yeah.
And the output is just the soft factor with the token.
Yeah, they're all pretty similar on that one. It's the update rule that's actually different. And so they say, I already said this earlier, so self attention with is basically KV cache grows linearly, unlike in an RNN where it's fixed. And so in an RNN you're compressing it into a fixed size every time. And to answer your question, TPT is fundamentally about learning how to do that compression dynamically over time instead of having a fixed thing that you did when you trained earlier. So they break it into, outer loop, inner loop. This has ties to meta learning. In meta learning, you want to learn how to learn. So what they're doing here is you have the outer loop, which is the regular training. So you're doing self-supervised, next token prediction, predict token, T given T minus 1, T minus 2, etc. And you do that, I think what they do is they just do that normally, like you're trying to neural network. But then when you're doing inference and testing, then you're using the inner loop. So I don't believe they're doing both at the same time, unless anyone inferred that differently. They're what?
Those are nested loops. Like one's
They're nested, but I don't know if they're doing this both. Well, they're doing it, yeah, okay. They're nested when you're doing it during training, but I don't think you're doing the outer loop and inference. I think when you're doing regular training or pre-training, you do both, and they're nested. But when you're doing actual like production level stuff, you just be doing the inner loop.
just doing one stuff.
Yeah. So the reconstruction is can you predict, the same given the input?
Yes, but you are, so in the outer loop though, you're learning your T0 time sets for the projection. Probably.
So they show in figure 6, this is like some pseudocode-ish, like it's like PyTorch. Python is now the new pseudocode. So they have, during the forward pass, you're actually doing a prediction of the token, and then you can construct a loss of that, right? MSE here is a loss. So MSE is a type of loss or error, and so they're comparing the training view versus the label view. The label view is constructed from the value, so that's the ground truth, and then the training view is from the key, so that produces the prediction. And so you can construct a loss here. This is the task that you're optimizing for. This is the layer definition, and then they call it OGD, online gradient descent, so it's like stochastic gradient descent. In the paper, they talk about doing batch, mini batch versus instance. So they said that when you do an update step every time you get a sample, then you can explore more of the hyperspace, but it's not as obviously as efficient. So, yeah.
What learning rate do they use for the inner update?
Not sure. I think that would be definitely the paper.
It's actually learned.
It's learned?
Yeah,
Okay.
it's learned during the outer training.
Okay.
Yeah, which is kind of interesting. I don't know the
So
details. I just saw
okay,
that.
it's weird that they call it like OGD then and not more like Atom or something, but yeah. Good. Yeah, so the new self-supervised loss is equation of 4. So this is the values of truth, the ground truth, and then this is the predicted. And you can subtract those like the altitude norm. You can compute the loss of the weights given the input sequence xt. I'm gonna go a little faster because we have 5 minutes. So the inner loop formulation is that. So we're f is a function that produces the output z, and it looks at the query, which is the input against, it's the queries and query values and keys, which is a projection, which is like a weight matrix basically. And you multiply that by xt, which is the actual token input, or label ID from the token input, and it does parameterized by wt, and wt is what we are updating in this case. Right, so we're not updating data q. Data q is part of the outer loop.
Just one question.
Yeah.
What is the label, the ground truth when you're doing online learning, when you're predicting the next thing? What is the label again? Like at test time?
So you have theta v, which is a projection from the values matrix,
Yes.
and you're doing a map model with x.
Yeah, but an x is the input.
Yeah. So you're doing a reconstruction of the same input. These are both the same x.
Got it.
Yeah. So it's a reconstruction loss,
Got it.
like in an autoencoder.
Yeah, it's a scale divergence.
Cool. Okay. So the main three contributions they brought up with this paper were these DTT layers, which is the top left there. Again, you're doing an actual prediction and loss estimation during test time, and then they said they created this linear version of it, and then they created the MLP nonlinear version of it, and then they did these tests over 125 million to 1.3 billion parameters. I'd really like to see this scale out with much bigger model sizes. And then they did some hardware efficiency tests. So they were getting some pretty fast results, given that all the LLM stuff they used VLLM, which is pretty optimized for serving, and so they were approaching that. They did some implementation for TPT to work with VLLM is when I took over the paper. So that's a pretty good contribution. Okay. Any other questions for the one?
Still sort of a higher level question, but I mean, I suppose they propose this TT thing to help with the RNNs,
Yes.
short-term memory problem. What would happen if you just made that hidden state layer just like a massive matrix, so it could theoretically store a lot more information inside that hidden state, and like it would still scale appropriately, but like,
Yeah.
is there stuff on that?
Well, that's what I was saying. Like, they only went to 1.3 billion, so you have to compare it. Like, when you get a scaled up hidden state, where at the higher ends of sequence lengths with a transformer, you can still outperform them, right?
Yeah.
So that's not really.
Because you're gonna run. So you're saying you're gonna run once you get it big enough, you're gonna run into the same problem where it's just gonna be a massive computation. Is that sort of?
Well, they're hinting at that here, where they're saying, look on the left, we can keep scaling up compute. Which allows us to run these bigger models on bigger sequences, and on the right on bigger sequences, and we're getting really high performance. And so what they're alluding to, I think what they're hinting at in this paper is what would happen if you got to something that was commensurate with those really big 4 or 5V models. And would it still, it looks like here it would stand up, but you wouldn't have this increased requirements of RAM and all that. And you have to make that trade-off, because when you're increasing cache, you're increasing RAM requirements.
Is this all happening on a single machine?
Not sure.
Oh.
Yeah.
This was a two-parter, kind of touching on your question. So for the RNN with cache, as well as for the transformer especially, one of its main strengths is going to be this residual stream going through. So the network can pick and choose exactly what it wants to augment with what layer. How does this, maybe I'm just not seeing it, how does this have the ability to have a do nothing function that we're just going to pass this through the residual stream?
It would have to do with the state compression.
Yeah, I mean, first of all, one of the critical things that they adapted to is they added a residual stream. So all of their models have a residual
Okay.
Okay,
That's
so
right.
they're the residual stream.
Yeah, and they found that to be critical for making.
Awesome.
What section is that in?
That is on page 4. It's at the top of the page where they have this table of naive RNN, self-attention, and then naive TDT.
And they did an ablation with and without residual.
It's in their ablation table. They have it, which is on page.
Yeah. So that's also something to
12.
call out in the paper, is that this is not just a vanilla RNN.
Okay. And speaking of naive, this question might be, does this vaguely remind you of a variational autoencoder? Because we're going in and augmenting the actual parameter space. To me, the outer layer is kind of describing, oh, here's the space of variations to the parameters that you have, and the inner layer is saying, oh, here's the probability distributions you're going to want to pick and choose from. At least to me, that's what jumps out.
Well, if you're trying to when you're doing your testing or sampling from a distribution, you're not really doing that here.
Okay.
There's just a forecast. But it's like an autoencoder and like the formulation of the reconstruction loss.
Okay.
So, kind of. Great. Any other questions?
So if somebody were to make like a 405 billion parameter model, what would the implication be? Would it be cheap inference for large prompts? Is that the kind of?
So it looks like you would just need less from the right figure here. It looks like you need less compute to achieve the same level of complexity.
Gotcha.
Yeah. So it should be more compute efficient, and it should, given you have a good enough cache size that performs well, you should be also lighter on memory requirements than the equivalent transformer. Yeah, which would be great. And I think again, like the online part of this is also great, right? So it's like also learning as it's being inferenced.
So are there any open source models for this available?
I think there's an open source implementation for this. Should be in the paper. Well, I will. If anyone's curious, I will just put that QR code up again. If you want to see the paper that we just went over, and then I want to. Yeah, we're right on time.
We can zoom in just here.
Sure. Okay. Feel free to come up. Great. All right. Now, thanks again. Now we're going into paper 2, which is I-JEPA. So if you want to open this paper up, this is the next talk that Alex here is going to do.
Thank you. Hello everybody. For those who don't know me, my name is Alexander. I focus on computer vision side, so a little bit different than what we saw before. And my presentation style is going to be a little bit different, less the paper and more kind of on the conceptual level, just walking through the idea of I-JEPA. What I want to start with though is just to maybe make a step back and talk about the autoregressive models first, and the idea is I want to just compare how autoregressive models are trained versus how the joint predictive embeddings are trained. With the autoregressive models, we basically have a concept where we have a sequence of values and we want to predict the next one. Within this prediction, we're going to assume that there's some kind of trend in the previous data that we're trying to capture with the model. And we have a little bit of noise that comes in for the next value. So there is some stochasticity involved that you need to take care of. But on a basic, on a fundamental level, you have prior context that gives you some kind of pattern, and you try to extrapolate it somehow into the future. The simple example would be the predicting tomorrow's weather based on the observations of how the weather was getting hopefully cooler and cooler and cooler. Now, within a LLM space that we really love, we obviously have the simple example of this task, which is the next token, next word prediction, where, as I mentioned, we have the context, and we're trying to, based on that context, predict the next word, and we have this famous example from many lectures I guess, where we have the famous cat, and then we can try to predict what the cat sat on, the mat, the chair. And as you can see, pretty much all these things can be a valid answer. So there is that stochasticity element that you need to account for. And within the autoregressive models, that's usually trained with the a little bit of a noise parameter, or the what do we usually call it? Some alpha, or not alpha?
Oh, epsilon.
Epsilon parameter that we can increase or decrease the randomness there. Was there a question? One of the important things here to notice is that we are focusing on predicting a specific word. We're not predicting a concept. The specific word can vary, so you kind of have to learn, in a way, the very intricate noise that could be inside of your data. Now, if we look at the joint predictive embeddings concept, the idea is different. The idea is that we actually going to try to predict an abstraction of the data, given the context. So we again deal with the context, but instead of predicting, instead of predicting exact value of a pixel in case of computer vision, we're going to try to predict what conceptually in that specific sector of the image might be. The visualization here is actually comes from paper where they trained a certain add-on on I-JEPA model that basically takes prediction of a
So you said that you're not predicting the exact pixel, you're predicting the general concept. So I watched a video where Jan can explain this really well. He said, let's say you have a video and someone drops a ceramic plate. What happens? It breaks, right? It shatters. You don't care, which flake of which piece of ceramic went in which direction. You generally want to predict what the outcome was. You wanted to know that it shattered the plate. And so at the representation layer, you would abstract away all the exact movements of those fragments, but you still get the same outcome, right? So that's what you actually care about.
I love this example. It's much better than these visualized plates. The idea here was to kind of say that it doesn't matter what on the background. What we care about is kind of the idea of the paws of the dog. But I love the example.
It's Jan Lipin's example. I'm no very
fair enough. So once again, JEPA, you focus on predicting the concepts that might be versus the order regression, you're predicting the finer detail that's supposed to show up in actual input. Now, digging more into the actual meat of the I-JEPA design, we basically starting out with 4 main concepts. We have the context block, which basically is a part of image in this case, that is provided into the model. Then we have targets. Those are the potential crops that we can carve out of the missing input and provide into the model as unknown targets that the model needs to predict. Then both of those, the context block and the target block, they go through their respective encoders, and there is one last piece, which is a predictor that sits on top of the context encoder, and it needs to predict what concept the target encoder needs to produce. Here's the example. So on the left side, you can see the original image. Then going from the left to right, we see the example of the context that's provided into the model. Then within the targets, it shows several examples of crops that being carved out of the space that provided into the model as the target. And the idea is that the model needs to predict what conception is supposed to be in this different type of targets. One of the interesting points to mention here is that once you create a target, the target is sampled from the image independently from the context. You might actually create an overlap between the context and the target, which is kind of trivial task to predict. So during the training run, the model basically rejects those trivial tasks and only focuses on non-overlapping targets with the context. Now, in terms of how the model is trained, the the way the model is trained is we're basically focusing on training this lightweight ViT predictor that basically receives the features from the context encoder, and this predictor is trained with simple L2 loss. Then the way we trained encoder, which is the most useful part for us, is actually we're just training end-to-end with the predictor. So we propagate the losses that go through the predictor into the context encoder. Now, what's interesting is that the target encoder is pretty much the same network with almost the same weights. The only difference is that to make sure that we don't have this mode collapse where both the target and context encoder produces the same values, they basically use the exponential moving average of the checkpoints to update the target encoder. So in this way, they kind of go away from the problem of mode collapse. And what this overall architecture does is basically, this is kind of, again, visualizations from the paper, what it can potentially learn. And the idea is that they try to illustrate that it just learns the concepts of what's supposed to be in the masked part of the image. But to visualize those, they train a separate add-on to the network on some sketch example to visualize this particular use case. It doesn't mean that the network actually learns sketches, it's just useful visualization of that.
Are the top and bottom images the same?
Yes, they are.
You can't spot the difference.
Where's the
This
wall?
was a test.
Good.
Remember, silence have the deadline tomorrow.
Now I do have a question. So it's basically like learning. You have a predictor block. So you have a target block and you have a context. The context has the mask tokens, and does the context have the mask tokens?
So it's ViT. So the context only receives the unmasked tokens. Only the part that we did not mask. So this part is not going into it, but the top and this little square goes into it.
So it's more like you're doing the loss between the representation, the link representations, and not the pixels, right? That's
correct.
Yeah, sure. Similar to like a clip type
Yes,
loss.
yes.
It's an L2 loss. But what do you like? What is the predictor actually predicting? Like, is it predicting like the positionality of
Correct.
the target inside the original context?
So the predictor receives the feature embeddings from the context that's visible,
Sure.
and also it receives the positional embeddings of what it needs to predict. So it receives positional embeddings, and then it needs to predict what's supposed to be there in that particular spot. So in this example, it's supposed to be here.
So your input is the actual feature space of the unmasked part, right? And then you're predicting as output the representation of the masked part.
So features of a masked part,
Yeah.
and positional encoding on masked part.
Is it? I thought the positional encoding was given.
That's what I'm saying, that they go
Yeah.
into the
Oh, they go-
predictor.
yeah.
And then you're basically doing L2 loss between the ground truth of that position versus the output of the predictor, like the embedding of the predictor that the predictor outputs versus the ground truth embedding of the
Versus the embedding of the target.
Yeah.
of the target, right?
Yeah.
So I want to move away from the idea of ground truth, because once you push the target through the embedding, what is ground truth? It's kind of, you just get an embedding of the target.
Sure. How does it then handle mode collapse? Like, what if like the target, like if you're just comparing embeddings and not the ground truth, like
Right.
how does it not just output garbage both times?
So, similar to self-distillation, the idea is that you basically keep different weights for the target and for the context encoder. And the difference in the weights that the target is the moving average of the context encoder. So that moving average makes the weights different. So they're supposed to predict slightly different things, so you avoid mode collapse. And that's how they've done it, and it worked.
Is that where the noise comes in?
Well,
Like the moving average is also
Move-
taking
correct.
noise.
But there is Jan LeCun has also a different paper, I think it's pronounced as ViT-Huge, which basically says that you can potentially train without exponential average. You just need to make sure that you have additional loss terms that incentivize diversity of predictions so that you can directly avoid fault problems. If that makes sense. Yes?
So this method sounds very similar to this other method called bootstrap your own latent. So I was wondering, like, what's the difference?
What is that? What is it called?
Bootstrap your own latent.
B-O-L.
Can't remember what the
something good.
acronym. Yeah, B-Y-O-L.
Yeah, B-Y-O-L.
Say latency, like latency?
Yeah, like
Latent
latent
space.
space.
Latent space. Yeah, like embeddings.
So I don't see here specifically, but they basically tried to compare several papers in the same vein. I think one of the main observations within this paper is actually the way you sample the target blocks is important. Specifically, they found that making the target blocks relatively big makes the model to learn much more useful representations that they prove afterwards that they perform on a linear approximation of ImageNet of the classifier model. They perform much better than the previous models. So the idea of training within the representation space is not new, but I think that the masking schema is kind of new that they proposed.
How do they prevent contamination?
Contamination of what?
Like if you're training it, or if you have labeled truth, then what if you over successive iterations you end up memorizing?
Label truth. So during training, they don't use any labels. What you are learning is what is supposed to appear where the target points you to, what kind of concept is supposed to appear. But they don't provide specific labels that it's a cat or that it's there's no labels, it's self-supervised learning approach.
Okay, so if you, let's say you're always blacked out, the far right side, and you always predict the far right side, then in the training data, it would never have any contamination. But if you're sampling all over the image, how do you keep it from having contamination?
This training, you said earlier that the training throws out the ones that are overlapped.
Oh, okay, so there's a pre-processing.
He said
so
that, I don't know.
when you select the contexts, so let's take a look on the top left example. You basically give the model essentially the top half of the dog space.
Okay.
And then you sample, for example, in that top half as well. So you have overlap with the context. In that case, you reject that target. You're saying, I'm not going to train.
Oh, okay, so that's why the targets you don't have the context part.
Correct.
Oh, okay.
Yeah, so, okay, I looked at the paper, and they shoved it into the appendix, and they really should not have, because I'm gonna actually explain how they sampled. I'm gonna actually tell you that they put a hack in this paper, and this is why it all works. It's not why you think. It has to do with the loss. It is not why you think it works. So first of all, they actually do the sampling for masking. They also randomly cut out parts and they'll rescale them too. So they're hoping that the rescales, as they blow up and shrink the images, will help. And they also chop up the image. They, like we said, they remove the overlaps. Okay, here's the interesting thing. You go to page 12, 8.1, it's called optimization. And I really never seen this setup, but it actually works. They train with a batch of 2048, which is absolutely insane. They take a learning rate from 10 to the -4, just standard, and they decrease it to 10 to the -3 in the first 15 epochs. That's not standard. They further go to 10 to the -6 right after. But here's their trick. they're running with Atom with a momentum of 0.996, and then they'd go all the way to 1.0, which means every Atom update has your full training set every single time. So they're just keeping all the training through the data set throughout the entire momentum of the training as it just sees newer and newer things. So their hack is you just take your data set and you just keep adding to the training sequentially your data, just like just like a transformer keeps adding tokens. So they just took a page out of LLMs and decided, why don't we just keep doing this with the laws? I think that's the real reason this works, is that you're just keeping all this context around. And so
that appendix for our resources is useful.
Yeah, pretty much. Yeah, so essentially you're keeping all the context you've ever seen in your optimizer, like throughout the whole run of your training. And that's why they're able to like do this, because you actually almost like learn a policy of just like how to get the concept. Because you keep your whole training like data set in the training, which typically isn't done. And that's their big hack to get this to whole thing to work.
Well, we need to talk. I would need to understand better what you're exactly saying. Or my hair, but
it's a weird deal.
If there's anything else,
it's very atypical to increase the learning rate, and because usually,
the other way, they decrease the learning rate while increasing momentum.
But you said they went from 1e to the -4 to 1e to the -3, so they increased the learning rate.
No, they went back to 10 to the 6.
Yeah.
This is one.
Oh, no, never mind, no, Zion's correct. It's 10 to the -4, then 10 to the -3.
It's kind of like a warm up.
Yeah, and then you're at 10 to the -6 really quickly after.
It's like a random
So it's this.
scheduler, yeah, very random scheduler.
No, this is standard warm-up and
Yeah. Yeah, you warm up, then you warm down.
Yeah, but it's not a warm up, it's 15 epochs, you said.
Yeah, it's 15 epochs.
It depends on the size of the data set, I don't know.
You usually do like a few thousand steps, not like they're.
Yeah.
It's not like.
Yeah, the data set is 250 million images.
15 epochs times 15 million images? Yeah, this is not one.
Yeah, they're cooking it. It's not a
Pretty much, they're like flash baking it.
One of the interesting comparisons that I noticed about this specific approach versus more or regressive approaches, specifically master encoder, is that it takes about 10 times less compute to train I-JEPA, and they indicate that it's because they don't learn specific fine-grained details that master encoder has to learn, because it tries to decode the actual pixel values.
Three, maybe you only talked about it when you speak, like how do they avoid collapse? Because I look at the papers, they say collapse to the issue, collapse to the issue, I don't see how they.
So they just they kept the weights slightly different by basically doing moving average for the target of the context encoder. So they basically have the weights slightly different, so they cannot converge collapse to one. So they use the context encoder and they store the checkpoints, and then for target encoder.
It's two different encoders on the same?
Exactly same network architecture, but the only difference that the weights are different by.
So there's some panelizing and regularization to keep them divergent.
Yeah.
Okay.
So target encoder, the only difference is that average of
so
context encoder.
it's fine if it's normally it's supposed to have the same weights, right? What is bad is that if the encoder basically output the constant, it's always zero, always zero, it's very easy to predict something that is always zero, right? But that's what we want to avoid.
Right, so if in the beginning we had a context that started outputting the same value, and we start averaging the checkpoints of that encoder, that would be bad.
Yeah.
I think the way they schedule the learning rates is specifically to avoid that early collapse of the context encoder. And then as the training progresses, they're making the average of the checkpoints to update the target encoder. So they would have slightly different representation by the target and by the context encoder. But like I said, there is a different paper again from Yang and Kuhn who is saying that you can actually avoid all of this by just adding additional loss terms that penalize for that basically encourage the variation of predictions so that they don't collapse to the same value. Yes,
so the I-JEPA, what kind of latency did that introduce if you integrated it into like the real-time mapping or you know, something where you're combining LiDAR camera data? Is it possible to stack that in to get more context?
So they use standard ViT architecture. I think they released ViT base and ViT-Huge model. So depending on your hardware, you can benchmark what is the latency of those architectures. But both of those networks available from their open GitHub repo. I think, I don't remember exact numbers, but we've tried the base model on something like V100, and we were getting something around like 20 FPS. But that base model, as you know, with any transformer architecture, you really start to lose in terms of the benefits and richness of the representations that runs compared to the big sister model.
But you know, I'm looking at on-device capability, like you know,
What device?
Yeah, it depends on the device.
Ideally, they're getting it down to like an iPhone or something like that.
Which iPhone?
So what they've done that was interesting is that they basically trained this encoder, which is the most useful part, and then they trained a variety of different prediction heads on top of it that could be used for different tasks. So for example, monocular depth estimation from just one image, or making those sketches that I showed before. So potentially I can see where you can have that backbone with the prediction head that you need, for example, depth estimation that you afterwards fine-tune with a smaller model for like transfer learn, and then deploy that transfer learn model on your device. So I think that would be.
You can also do model distillation. So you can do like random inputs, produce the output, and then use that as a training signal to train a smaller model. But I think what they're doing here is more like, can you build a representation space to do prediction? Because like the whole point is like in a transformer, when you're doing next second prediction, you get a compressed perspective of the whole world or whatever the training data is. So they're trying to do that with vision, basically.
One more thing to mention is that this paper is relatively old, like in our machine learning. What's interesting is that when you see our llamas that come out, they train the big model and then they distill the big model to smaller models for serving or for people to use. This was much more of a research paper where they didn't do that. They kind of trained checkpoints, they released them. Additionally, they trained these checkpoints on ImageNet versus if you look at other papers that Meta produced, for example, Dino V2, they scaled data sets for that model significantly where you have much more richness because the data sets are bigger. So this paper is good demonstration of the concept that you don't have to learn fine-grained details, but it's not production-grade model yet.
I think that the JEPA model is just a ViT model, right?
Yeah.
Yeah, so if you can run ViT on a phone, I mean, this is just the training stuff. It's not, the model's not any bigger than a ViT model, so I think you can just run it as a standard model on the phone. And you can't do the training on the phone, of course, but you can just run it. It's just the same model.
You can initialize it directly from the Python.
No, not yet. Can they add any inflation studies on how the model does on like slightly noisy data? Because one of the big things about like MAE and type of approach is because, for example, we used to have a lot of issues with like hands and 6 fingers, right? And because it was predicting the pixels itself, it started learning that you have like those 5 fingers. I'm wondering, because now you're doing prediction on the representation of those, it might not have the information whether it's like 5 fingers or 4 fingers or 3 fingers or 6 fingers. Do they have any ablation on some of the like noisy nature of pixel level stuff?
I'll be honest, did not dig into the paper kind of like ablation part like that deep. I kind of was more interested in how quickly you can train the model, things like that. So I'll have to get back later to you.
Like, stuff like this, like it would work well on ImageNet, which is like single instance, like single object, but I don't know how well it will work on like more granular information tasks.
I think again, granularity, I think is the key word, because they're learning high level concepts, kind of in a way lose granularity.
Well, once it predicts as an embedding, can't you use like a really good decoder that has an understanding of 5 fingers?
Depends on how good, like if they encode that information in the model, like if that level of granularity is encoded in the model.
Well, it would encode that it's a hand, and then the decoder would say, oh, a hand has usually 5 fingers.
Yeah, at that point might not just use something like M80, which is directly doing it at the pixel level.
Well, because when you do reconstruction on a pixel level, you can get really huge losses, but the representation is still good.
So their key argument is that it takes you 10 times less to train, and the accuracy, at least on the ImageNet linear evaluation, is higher.
So how does M80 do it?
This pixel level reconstruction, and the thing with like this type of approach is like you lose some of your granularity, even in the representation that you might get, which is why when we had BERT-like models, they were not as good for next step prediction, like versus like transformers.
Okay, so here we're directly saying we don't care about granularity, we care about high-level concepts.
Yeah.
And those concepts used for full classification tasks. For the generation task, that's different. If anybody wants to connect, here's how to find me. Let me know if you have any other questions.
Okay, so you're welcome to stay here for another 29 minutes. I will, you can keep talking downstairs in the lobby. We usually would go to the bar, but why give them revenue? No, I'm kidding. But it's really loud in there, it's hard to kind of talk. So it's just better to go downstairs near the elevators where you came up from. There's some couches, you can just keep talking. If security tries to kick you out because you're here till midnight, then you can go to the bar. But yeah, after 9, or you can stay there from like 9 o'clock to 10 usually. If you haven't, if you're new here especially, or if you don't have, if you haven't joined the group on Meetup, please do so you can actually get email notifications whenever we do these. Okay, I think everyone already does that. And then there's a Discord, if you want to join that. Mostly in person, but you're welcome to join Discord if you want to like suggest a paper idea, or if you have any questions and follow-up stuff. Okay. And lastly, if you want to give a talk, you can also talk to me in person. I'm here right now. If you're a researcher, whether it's in industry or academia, especially if you want more people from academia to come. We usually get a lot of startups, people at big companies, which is awesome. Also, if you're in academia, please let me know. It doesn't have to be a paper that you wrote. We didn't write these papers today. We've had people come in the past who've written the papers as well. So we're open to both, but if you just want to give a talk on it, refine your ideas, it's also get live streamed and on demand, so you can also like use that for cloud, I guess. Yeah, just let me know. Thanks again to Apple Factory for having us. Thank you, everyone. perhaps.
When you say project, are you Has it not already been done? That's cool, but it's a different application. Well, that's cool. And it was a little bit, not too nice. Because it was hard to find on the website. Like, I had a hard time finding information. He's like, you need to try harder. You need to read 1,000 pages. You know, like, I don't know how many people are going to try. I just came here to so I was here the whole time. Basically an AI
It's an so the wording we just chose we did it twice. I was there for like 7 years. Now it's
Microsoft is not in the business of being
It's been interesting playing with them. Really good reaction. I haven't used it. This is in ChatGPT because it's homework we're doing. So it's screenshot, bank statement, screenshot, balance sheet, pronunciation, do that. Sure. Okay, I'm going to try that. Yeah, I think it's in the end, it's all AI models talking to AI models. It's AI models all the way down. Let's say someone uses GPU cluster for like, what, I think it's another. Okay. So I did the sort of. Okay, yeah, I saw Steve. I catch him every other week. So I told him that you said you wanted to go like stand places and do. He's like, yes, that's called stand. Like, yes, like that. So yeah. Did you buy an elephant gun?
Okay. They told me to get a really low caliber one because it's
See, this is where the crypto bros come in. Yes, so they're like,
I'm gonna hard
You run the app on your machine, and then it's all like, your machine to use your machine. They're like a big
well, yeah, Steve's got a whole building where he makes jerky out. It's a whole thing, they drink and they make meat. So yeah, so you're on the list there.
What's up with the
And, based on your shotgun experience, well, yeah, I'm like, you might do a television show up when he's gonna show up with a moose gun. Because these deer around here are like dogs. Yeah, you see them around my yard or whatever. Like I'm from the Northeast where like deer are big.
I'm like, my AR and it's good. Like, get like a bolt action. I was like,
You I know nothing about it, but we have friends with the ranch.
That's my only
That's the thing.
he's gonna cry.
These people are taking the code and running it on their network.